So, thanks everybody for joining. This is a presentation of, I've actually changed the title from just talking about one of our projects to giving you an overview about a sampling of the projects that we do here at ESRL, but ones that can specifically concern sea ice and ones that are specifically striped interagency. So we are going to talk about our Arctic Indicators project. That was a collaboration between NOAA and NSIDC predominantly. And when Walt was at NASA, we were affiliated with NASA, which is how we started, but he's at NSIDC as well, and our university partners. I'll talk a little bit about where we're at with the GlobalArcher initiative, which is very much a NOAA, NASA, Coast Guard, Navy, and university and international partners project. We'll talk a little bit about a US AON project that also is an excellent interagency project involving, again, NOAA, NASA, NSIDC, and Navy and university partners. And then we'll end with what the original title of this presentation was, which was talking about some of our work on sea ice forecasting. And I put sea ice in quotes there because it's more than just sea ice, of course. It's full coupled ice, ocean, and atmosphere products. And then end with some of our collaborations that are associated with that specific forecast project. And our partners in that are DOE, Los Alamos, Navy, and our university partners again. Okay, so the first one I want to talk about is Arctic Indicators, and you can see the list of authors, and we are, I said submitted to Climatic Change, but we're going to submit it next week. And I just wanted to, I don't have to really explain to the people on this call the fact that the Arctic is changing in significant ways, but this paper is really aimed at addressing the fact that although we've been able to articulate that the Arctic is changing in significant ways, we haven't been able to create a significant or comprehensive set of well-established or regularly tracked set of indicators. And indicators in this context are things that are simple to understand, visual bits of information that improve a wider range of stakeholders' awareness and information that can support decision-making. So this paper is aimed to provide a set of indicators that we recommend based on a certain set of criteria. And we used this conceptual model of the Arctic climate system to guide us in our selection of these indicators. And a lot of the things that we have done as a community, and people on this call specifically, have put forward information through the Arctic report card, but this is even going one step beyond that. Okay, so without going into our entire process, the author team compiled a broad list, and what's the background of this slide is just showing you actually a subset of even the broader list, where we queried the literature and found existing indicators. We prioritized what we found and down selected them using the conceptual model as our guidance. And then we identified indicators that we wanted to recommend so that we could really, as a community, be able to track the key climate-related changes on a year-to-year basis. So this is the list of the indicators that we recommended. And we used we visualized it with this kind of bullseye graphic to show the different sectors, biological, socioeconomic, and physical, and then each of the indicators that fall within different kind of spatial scales, going from community in the center of the bullseye to regional to pan-Arctic, to kind of give you a sense of how they are distributed. And the ones that I've listed in blue are the ones that relate to sea ice. Okay, moving on to our second project, which is developing an initiative using the Global Hawk. The Global Hawk is pictured up there in the upper right. It is about the size of a 737 and it flies unmanned. So we being NOAA, Coast Guard, and NASA predominantly, are working to develop 3 priority missions so that we can demonstrate the utility of using unmanned aircraft to provide more enhanced information in 3 different topic areas: maritime awareness, sea ice, and Arctic weather. So just a little bit of background is there has been 1 Global Hawk mission to the Arctic, and that was in March of 2011. In the upper right, I've kind of circled a triangle above the North Slope of Alaska where we were able to release 35 sondes. And this was a real technology demonstration. It had never flown quite that far. And you can see from the track that it starts all the way in Southern California. So in this particular flight, it transited a atmospheric river feature, which is where that red arrow was, goes up and captures this low off of Canada, goes all the way across Alaska, and then was able to provide information where we dropped the 35 sondes. When we were able to get up to the Arctic, we were lucky enough to transect a polar vortex that was associated with, at least at that point in time, the record level ozone loss. So the temperatures were as low as we had measured in, I don't even know how long. We get like Tom's satellite information up there, but it was a very lucky flight and it was fortuitous. And we also crossed a lead, the flaw lead that is off of the North Slope of Alaska. And we were able to look at the boundary layer because the dropsondes get very high resolution information on wind direction and speed, specific humidity and temperature. So we were able to identify the difference before the lead and after the lead about how the boundary layer changed because of that feature. Okay, I have one slide that is also a very nice interagency effort that Sandy Starkweather is leading for USAON, which is developing a consistent set of requirements for sea ice thickness observations, or I would almost rename that products. And this is aimed towards the forecast services in mind. So what we want to do is be able to, sea ice thickness has been identified as such an important initialization field for forecasting sea ice. It's something that we have not had consistent information on. There is a variety of ways to get at it, and there will be new satellites coming on board next year with ISAT-2. So we have kind of inconsistent or different methodology, different sensor information, but nothing that's kind of a consolidated technology neutral, as we call it, product that is low latency so that it has a quick turnaround time, that it is and has kind of uncertainty fields associated with it, so that when you're using it in your models, you have forecast guidance that has some sense of uncertainty associated with that. So that's something that we're working on with a larger team, and Rick is on that team as well as some other people on the call. Okay, so now we're going to end this kind of lightning talk with what the original title of this webinar was called, which was Improving Sea Ice Forecasting in the Marginal Ice Zone with a Coupled Regional Model. So we're going to go, we're going to talk a little bit about the model development, issuing experimental forecasts, how we're evaluating the model with an eye towards improving the processes and some of our R2O activities. So I think I'm going to let Amy take it from here. Okay.
So the model that we're using for our forecasts is called RASM-ESRL. It's adapted from the Regional Arctic System model, which was a regionalized version of the CESM. So it has all of the components of the CESM, except for the atmospheric model, which the CAM, which is the NCAR atmospheric model, has been replaced with WRF. And we've upgraded all of the components since we originally got the RASM model. We're running it on a 10-kilometer horizontal resolution within all the components. And we've increased the domain relative to last year's forecast to include the whole domain that is necessary for simulations of mosaic, for the mosaic year, since we will be playing an important role in providing daily forecasts to the polar stern during the mosaic year. We are initializing the model with the GFS atmospheric analyses, and with the satellite sea ice analyses, we're using AMSR2, Cryosat2, and SMOS. So we've been experimenting with different ways to initialize the sea ice concentration and the sea ice thickness. And we use the 3-hourly GFS forecasts at the lateral boundaries, and we run the model for 10 to 16 days. So we have these 10-day forecasts run every day from the end of July to the end of November, and we make them available on the web page, our NOAA-ESRL web page, which is shown here on the right. And I don't know, I guess, should I go to it?
Probably not.
So we make available every day animations of different sea ice products, ocean products, atmosphere, and coupled fields. And for example, we look at different products like melt ponds, which are very important for the evolution of the sea ice. And we look at some of the coupled processes, such as potential vorticity at the tropopause and its impact on the surface, as well as other really important coupled fields to try to see, get some information about biases in the simulation of these processes. We're also working with the National Weather Service to understand what animations they need for model guidance and when they're constructing their sea ice forecasts. And so we have a set of animations specifically on the Alaska region for their use. We also have meteograms for a number of the ISOA stations, which ring the Arctic, as well as at some of the mooring sites, such as in the Bering Straits and in the Beaufort. And we also include some time height cross sections, which we initially created for the Sea State campaign, and they found very useful for their guidance. And it includes cross sections of where liquid water is in the clouds. And that's really important for understanding, well, the processes, number one, but we're also looking into whether we can use this to construct fields that are useful for animation and for aviation, and to understand where icing would occur. We also provide a subset of the model output on our archive, which is available every day. And we're getting quite a number of users, from scientists to lay scientists, and people are downloading the data and giving us feedback on what's useful, what's not useful, and what we will use to change what's available next year. So I'm going to focus on the evaluation that we've done for 2015 forecasts, because there was a really interesting campaign that we were involved with called Sea State. The track of the Sea State campaign is shown in orange in this figure here. And so the Sea State campaign took place in the marginal ice zone primarily in September and October. And it took place while the sea ice was freezing up. And there was a very intensive database of CTDs and sea ice properties and atmospheric soundings that we're using to evaluate our coupled forecasts. And the dots here are showing the regions, the ISO stations that we are also using for our evaluation. So this is showing a comparison. This is just to illustrate the interesting comparison of the sea state soundings in the upper figures. So temperature on the left, relative humidity on the right. The model is in blue and the soundings are in orange. And in the lower figure is showing the sea ice concentration. Again, the ship is in orange and the model is in blue. And this is just to show that we found that the model has really good correspondence to both where the sea ice concentration, the variability, as well as the atmospheric structure. And on the right here is showing AMSR2 are the colors, and then on top is the track of the sea state campaign. And the upper figure is October 14th and the lower figure is October 27th. And this is just to show that the sea state campaign is providing a really important database for the variability during the freeze-up period, which is our time of interest, since this is the time that we really need to know, we need to be able to forecast the variability of the sea ice for model guidance. And this is showing a comparison of the observed surface fluxes during the sea state campaign compared to the model forecasts. And this is for a 4.5-week period. And so this is just showing that, so on the left here is showing the radiative fluxes, long wave in the upper left, short wave down in the lower upper right, and then the turbulent fluxes in the lower left, and the total atmospheric flux in the lower right. And the lines are showing the observations, and the X's are showing the forecast from 24 to 120 hours. And this is just to show that the model is doing a really nice job of simulating the synoptic variability. If you look at the long wave down in the upper left, there is an interesting bias that we're looking into. During clear sky, we are underestimating the long wave down fluxes. That's an interesting bias that we want to understand better. But this is just showing that the model is doing a really nice job of capturing the synoptic variability and the radiative fluxes, which is an indication that we're simulating the amount of liquid in the cloud correctly during this period. So this is a really interesting diagnostic that we're looking at. It's a way to visualize all of the data that was taken during the sea state campaign from the CTDs in the ocean, which are shown in the blue, to the surface measurements, which are shown with the light blue, to the atmospheric measurements with the soundings, which is shown with the red. And this is just showing a nice way to see the biases in the atmosphere. So this is comparing the GFS to the soundings, showing a way to identify biases in our initial conditions for the atmosphere, as well as the biases in the ocean, which we are looking into very carefully to understand whether the structure of the temperature below the mixed layer is being represented adequately in the initial conditions, and how important that is for the forecast. So this is showing our comparison with some of the buoys. So this is, if you look at the right figure first, the black dots are showing the location of the buoys. The color is showing the skin temperature. So this is a way to understand whether including coupling with the sea ice, allowing the sea ice to evolve over this very short time period, is improving our forecasts. And so the dots here are showing the data from the buoy. The red lines are showing the GFS analysis. The blue lines are showing the GFS forecasts. And the black line is showing the mean of 5 RASM-ESRL forecasts, and the dashed lines are showing plus or minus 1 standard deviation. And this is just to highlight that within the ice pack, the RASM-ESRL forecasts have this equivalent skill to the GFS forecasts. But for buoys, this is showing a buoy in the marginal ice zone. So this is showing that when you allow the sea ice to evolve in time, we are actually able to improve our forecast. If you look at the lower right, this is surface temperature. The GFS forecast shown with the blue cannot capture the rapid drop in temperature because of the change in the sea ice, which if you look at the black line, the RASM-ESRL forecast is able to capture. So this is just showing that it is very important to allow the sea ice to evolve on these very short time scales to be able to forecast beyond 7 days. And so this is just showing some process evaluation at Barrow. So this is just, if you look at the middle figure here, this is just showing that when you compare the Ravensons on the left to RASM-ESRL on the right, there is such large uncertainty in estimates of ice water content and liquid water content that we decided to try to evaluate when and where liquid and ice was forming. And this is just to show that liquid in the, this is August 2015, liquid is forming in the Ravensons. We're able to simulate that quite well as the where and when ice was forming. So we're coordinating with NCEP to try to understand first how complex an ocean we need on these very short time scales. And to do that, we've partnered with an Italian ocean assimilation group to try to include all of the in situ data to try to have a better representation of the ocean structure and to see how important it is to include that structure to be able to forecast on these short time scales. We also want to understand how important it is to have these high resolution simulations relative to the NCEP global model. And we're also working with them to develop a set of baseline metrics that we can use when they're evaluating the NGGPS, the next generation global forecast model. We're also working very closely with the National Weather Service, the Sea Ice Desk in Anchorage. We're doing, and I'll just talk about our ensemble product evaluation. We're doing a number of different projects with them, but if you look at the figure on the right, this is showing some of our ensemble forecasts. So this is during the meltback period here. So this is starting on August 10th to August 26th. And then a second set of forecasts would start on August 27th to September 12th. And so the first set of forecasts is experimenting with the uncertainty due to initial conditions in the sea ice, so sea ice thickness. And the second set of forecasts show the uncertainty in the atmospheric conditions. So this is using 5 GFS forecasts as initial conditions. And this is just to show some of the work that we're doing. The X's here show the MSR2 that was observed at that time. And that's also a big issue that we're looking into, to what extent there is variability in MSR2 due to conditions such as melt ponds, and how to take that into account for our initial conditions. So thank you, and we're happy to take your questions.
Thank you, Janet and Amy. That was really nice. Really great presentation. And yes, are there any questions? I think we have time for a few. Don't be shy. Okay, I have a question. Janet, on one of your earlier slides, you were listing priorities, and one of the categories was aspirational. And I'm wondering, what does it take to upgrade from aspirational in terms of your priorities?
Yeah, in the aspirational category, that means, so we had a list of criteria that we had to hit. And I'm actually going to, well, I have that criteria. I guess I can't bring it to the forefront, but one of the criteria is that it has a data set that is ongoing and that there's somebody committed to its stewardship. So aspirational falls in means that it hits some of those indicator criteria, but not all of them. So maybe it doesn't have a champion, like the data is being collected, but nobody's ever actually created a product for it. So what we're saying is that we would recommend it, that even though it only falls into aspirational, we would recommend it still being, still having a commitment to it.
Great, now that's really helpful, thank you. Are there any other questions?
Yeah, on slide number 3, this is Jeff Curry in Fairbanks. On slide number 3, am I correct that essentially the numbered 3, that the gist of this is to create a set of standards for reporting and forecasting sea ice thickness?
Slide, so this was slide 3?
The one that followed is the one that led 2 more. Well, 3 more.
This one.
Yes, this is essentially creating a set of standards.
I would say less standards, but more recommendation towards that's built from stakeholder and operational forecast from the community.
Okay.
Things that are needed. So in addition to everything else that's being produced, to have one set of observations that could provide the input that's needed for the operational forecast centers.
Okay, I see. Thank you.